When studying real numbers, we evaluate sequences of individual points. But the problem changes when we examine an infinite family of complex curves. We need to know if a chaotic flurry of functions will eventually synchronize into a stable, predictable limit. This investigation starts with the Bolzano-Weierstrass theorem. For real numbers, any sequence of points trapped inside a bounded region must cluster together, guaranteeing a convergent subsequence. But does this logic apply to function spaces? Suppose we have an infinite sequence of continuous curves, strictly bounded between y equals m and negative m. Does every such sequence contain a subsequence that converges uniformly to a limit function? It does not. Simply capping the vertical height of a function tells us nothing about its internal geometry. To manage infinite families of functions, point-by-point boundedness is insufficient. We have to regulate how these curves oscillate relative to one another. In function spaces, our points are entire curves. This requires more stringent metrics to define the distance between objects. Evaluating a sequence's height at one fixed coordinate is a local test, but checking its geometric shape across an entire domain is a global requirement. Uniform boundedness only ensures the curves do not escape to infinity vertically. To see why a vertical limit isn't enough to ensure uniform convergence, we can examine a sequence that remains bounded while becoming increasingly erratic. Walter Rudin provides a counterexample in 7.21. The sequence is defined as x squared divided by the quantity x squared plus 1 minus nx squared. On the interval from 0 to 1, the denominator is always greater than or equal to the numerator, meaning every function is bounded between 0 and 1. Plotting the first terms, a peak forms at x equals 1 over n. Here, 1 minus nx vanishes, so every curve hits a maximum of exactly 1. As n increases, the peak slides leftward, becoming infinitely steeper. Despite the vertical bound at y equals 1, the horizontal width of this spike vanishes, causing the derivative to grow without bound. Because every curve eventually spikes to 1 near the origin, no subsequence can converge uniformly. This traveling spike demonstrates the failure of mere boundedness. We can contrast this with pointwise convergence to see the problem more clearly. If you fix a specific x and hold it still, the traveling spike will eventually pass it. Once it passes, the value at that x drops and stays near 0. This local behavior is the basis for Theorem 7.23, which uses a diagonalization method. The theorem proves that for any pointwise bounded family, we can always extract a subsequence that converges at every point on a countable set. However, pointwise convergence is too weak to ensure the curves maintain their shape. Because the spike always reaches a height of 1, the maximum difference between the functions and the limit is always 1. No matter how large n is, uniform convergence is never achieved. We need a property that prevents these traveling spikes by restricting how much a family of functions can oscillate over a small distance. That property is equicontinuity, as defined in 7.22. In standard continuity, we find a delta keeping the function within an epsilon margin. Usually, that delta depends on the specific point x and the specific function being used. Visually, an epsilon box represents vertical error, with a delta width keeping the curve inside. Equicontinuity requires a single delta width that works for every function simultaneously. Testing our traveling spikes against this, they fail. The spike eventually becomes so steep it breaks out of any fixed delta box. This establishes a universal limit on the steepness of the curves. It ensures that the entire family respects the same continuity constraints. By preventing slopes from growing without bound across the sequence, equicontinuity allows a bounded family to converge uniformly on compact sets. Theorem 7.24 proves that this universal limit on steepness is an inherent property of uniform convergence. It states that if a sequence of continuous functions converges uniformly on a compact set, that sequence is necessarily an equicontinuity family. The proof uses the triangle inequality to split the total variation of a function into 3 parts. Uniform convergence bounds the distance between the sequence and its limit, making the first and third segments smaller than epsilon over 3. The middle segment is controlled by the uniform continuity of the limit function itself, which is guaranteed on a compact set. This shows that equicontinuity is not just a useful definition, it is a required condition for any sequence that converges uniformly. This concept is central to the study of function spaces and higher dimensional analysis. It leads directly to the Arzelà-Ascoli theorem. This theorem uses equicontinuity to characterize which subsets of continuous functions are compact, mirroring the Heine-Borel theorem for Euclidean spaces. This property is used to prove the Peano existence theorem, guaranteeing that solutions exist for initial value problems in differential equations. By requiring equicontinuity, we gain the ability to extract convergent subsequences from infinite sets of functions. To summarize, equicontinuity allows us to control the behavior of an entire family of functions at once. Boundedness alone is not enough. We need a delta that works uniformly across the family to prevent steep spikes from destroying convergence. Establishing this property provides the necessary conditions for the most rigorous results in functional analysis. If you want more deep and structured explanations from books like Rudin, including every theorem, proof idea, and example, don't forget to like, subscribe, and continue your journey into higher mathematics.